Hi, welcome to the class. Let's continue our discussion on nuclei. So we were discussing about the nucleus. So what we are going to discuss today is a very important aspect and an interesting one too. So this is about the mass defect. Mass defect. So as the name is telling you, there is a defect in the mass, right? So what kind of defect it is? So basically what happens is when this concept goes like this, if I take an example, if I have one nucleon whose mass is 1 gram. So let us say that is neutron. So I am taking it as a neutron, that I have taken one neutron whose mass is 1 gram. Similarly, I am taking a proton whose mass is 1 gram. Now, if I combine these two to form the nucleus, what should be the mass of the nucleus? So, an intuitive answer would be 2 grams. But that is not the case. Actually, the mass of the nucleus is a little less than that, right? So, in this case, I am assuming the mass of the nucleus to be 1.5 gram. As I told you, that the mass of the nucleus is not equal to the sum of the individual nucleons. In this case 1 plus 1 should be 2, but that is not the case. It is little less than that. So I'm taking for our discussion of example, I'm taking it to be 1.5 gram. So the mass of the nucleus after combining these two is 1.5 gram. Now as you could see, the mass of the nucleus is little less than the individual masses of the nucleons, right? So where does this mass go? 0.5 gram. So first of all, you should understand that how to calculate the mass defect. Then I'll tell you where this mass is going. So how to calculate the mass defect? So mass defect in this case is 0.5. So what is mass defect? So mass defect is basically the decrease in the mass when two individual nucleons are combined together to form the nucleus. So this decrease in mass is what we call the mass defect, right? So basically, how do I calculate this mass defect? So mass defect is denoted by delta n, which is the change in the mass. So in this specifically, it is decrease in the mass if you are forming the nucleus. So delta n, that is mass defect, is equals to, so the number of protons is represented by, number of protons is represented by Z. What is Z? Z is the atomic number. So Z is the mass, Z is the number of protons. So if Z is the number of proton, I am taking the mass of the proton to be mp. So mass of one proton is mp. Z number of protons plus number of neutrons, you know that it is A minus Z, which is discussed earlier before this class already we had discussed that. So A minus Z m into n. One mass of one neutron I am taking to be m into n. Total number of neutrons is A minus Z, therefore the total mass of the neutrons will be A minus Z into n. And then minus mass of the nucleus. So this is the mass of the nucleus. I will be writing it as N, capital M and capital N. So right now I have written it completely so that you could understand. So this will be the formula for mass defect. This is the formula for the mass defect. Now guys, listen carefully that this mass defect or this mass is always given in atomic mass unit, or sometimes we write it just unified mass, that is U. Right? So this whole mass has the unit back. Now where does this mass basically go? So we know that when we want to combine these two protons, they will repel each other. Like if you want to combine two protons, they will repel each other. In order to overcome that, you have to do some external work. In order to overcome that force of repulsion, you have to do some external work. And to do that work, you have to apply some energy. So that mass is basically getting converted into that energy which is required to bind these nucleons together inside the nucleus, and that is what we call the binding energy. So what is binding energy? Binding energy is the amount of energy required to bind the nucleons inside the nucleus. And how do we get that energy? That energy comes from that mass defect, right? And that's how this binding energy will be equal to delta mc square according to Einstein's famous equation. So delta m into c square becomes the binding energy, and this energy is required to combine the electrons, right? Now this binding energy usually is in million electron volt. This binding energy usually is in million electron volt. So now the mass is in U, but binding energy is in million electron volt. So how do we convert this U to million electron volt? So basically it is 1 U into C square is equals to 931.5 MeV. So you have to convert it this way. 1 U square into 1 U into C square will become MeV, right? Or if you want, you can write it 1 U is equals to 931.5 upon C square MeV. So whatever number of U will come here, I will just multiply that number by 931.5 upon C square and it will become into MeV. So that is the whole discussion. Now let us do some numericals based on this. So the first question, and mind you that in the previous videos description section I have given one practice paper. There also you can find some questions to do, and notes are also provided there, right? So the first question, I shall remove this. So the first question is, you have to obtain the binding energy of a nitrogen nucleus. The nitrogen nucleus is 740. So first of all, you should know what are the number of protons there, what are the number of neutrons there, and what are the number of electrons there. And that I hope that you understood how to do that part, right? Now the mass of the nucleus is given. So I will write mass of this 7N14 is given, which is 14.00307, right? Then the mass of the proton. Mass of the proton is given, which is 1.00783 U. As I told you, mass is always in this unit. Mn 1.00867 U. Now use this formula to find out delta M. This. So delta M is equals to Z. How many protons are there? 7. 7 into 1.00783. This is the mass of the proton, plus A minus Z. A is this, Z is this. So A minus Z, 14 minus 7, that will become 7, into mass of 1 neutron, 1.00867, minus mass of nucleus. How much is the mass of nucleus? Mass of nucleus is this, minus 14.00307. And guys, this whole thing is in unified mass. That is it. Now if you solve this, you will get the mass defect. So I am leaving it up to you. How do you do that? So this will give you the mass defect. So I know that you people will be able to calculate this. This is just simple calculation. And shall this part as well I'll remove. And if you calculate this after multiplying and solving, you shall get the mass defect to be. And I want you people to calculate it. Just don't copy it from here. 0.11243 U. But I have to calculate the binding energy. So binding energy formula I will write delta mc square. But you know that the binding energy has to be in MeV, which is million electron volt. And therefore, so delta M, but I have to convert this U into that, and you know how do we do that. We will multiply this by 931.5 upon C square. So this is 0.11243 into 931.5 upon C square into C square MeV. So by multiplying with this factor, it has converted this U into MeV, and C square goes off. Now if you multiply this your answer will come in million electron volt, and kindly do that part as well. It will be 104.73 MeV. So this is there, right? That is one question. Now I will give you one more, and you people can do it. This is for the iron, and mind you that iron has the maximum binding energy. Maximum binding energy iron has, and it is one of the most stable atoms. You will learn about this in the next class, 26 Fe56. This is one whose binding energy you have to calculate. So I am not going to discuss about these things. I am just going to put the data there, and you people have to do it. I will give you the answer also. And this is something DI83209. And I'll write rest of the things. Mass of the neutron is 1.008. So in this case a little bit of change, mass of 1.008. They have continued this, so 008,665 U, and mass of the proton 1.007,7825 U. So this data is there. Now what are the other things which are given? So mass of Fe and mass of this thing are given. So mass of 26 Fe56 is given, which is 55.934939 U. This is 26. And mass of 83 Bi209 is given. This is 9, that is 9, 209. This is given 208.980388 U. So these are the two things which are given. And of course you know that you will convert this U into that, right? If I write the answer, then binding energy first part for iron, binding energy in MeV would be 492.26, and binding energy for this part answer would be 164.0.26 MeV. I want you to calculate the binding energy per nucleon as well. Now what is that? How many number of nucleons are there? Total number of nucleons? We know that total number of nucleons are 56, which are represented by the mass number. Mass number there is 56. Divide this by 56. Similarly, mass number, binding energy per nucleon for this. What are the total number of nucleons? 209 divided by 209. So what I was telling you, that iron has the highest binding energy. That was the binding energy per nucleon. So here you could see that the binding energy of this nucleus is more as compared to the iron. But if you calculate the binding energy per nucleon, then in that case iron will have a greater value, and it has the maximum binding energy per nucleon as compared to any other nucleus, right? So I hope you will be able to do these two questions, and one question is there in the practice paper, which is given in the description section of the first video of this chapter. And that is it for the day. Thank you so much.